So in linear spring part 1, what we understood was this. So we have a rest spring. The length of the rest spring is L0. And then when you hang an object, it comes to this position. It comes to this position. So when the mass comes to this position, the forces acting on that would be mg, and then there will be a force which we call Fr, and that is called restoring force. So now this situation is equilibrium situation. So this situation is equilibrium situation. Now this distance is going to be x0. That's the extension, right? So restoring force is acting on this. Restoring force is acting on the spring. This W or mg is acting on the mass. Acting on mass. Okay. So now, if you think about the spring, right? Consider spring only. Consider spring only. So if you consider spring only, then what are the things you can observe on the spring? Fr, x0. Those are the observables for the spring, right? Observables. Observables on the spring. Okay? Observables on the spring. Now, since the system is at equilibrium, right? System is at equilibrium. So since the system is at equilibrium, that tells you that forces are balancing each other. Forces are balancing each other. Right? Because of that situation, you can say Fr restoring force is proportional to minus x0. Now in part 1, I discussed about this minus. This minus is mainly due to the direction. x0 is measured in this direction. Fr is moving this direction. So you can see the direction mismatch, right? So this x0 is the extension, and then minus is the direction. That is due to direction. Now we know that how to convert an inequality to a equality by introducing a constant, right? Constant k0, right? So in this description, this k is considered to be spring constant. Spring constant. So the spring constant, this depends. This depends on the material. So it's a material dependent constant for copper, for brass, for iron, This K value is different, and X0, FR values are different accordingly. Okay, so this is what we discussed in part 1, right? So now if you think about physics, the fundamental physics consists of two things. Fundamental physics. Fundamental physics consists of two things. So any topic, any question can be discussed under these two conditions. The first one is force. Force. Newton laws can be applied, right? So we know about forces. The second one is energy. So this physical world is about forces and energies, right? So if you think about the motion lesson we discussed from the beginning, we talked about forces, we talked about energies, that's it. Now in this lesson, what we discussed about the forces, right? So we discussed about this restoring force. We discussed that. Now, what is the energy description now? So now we are going to think about how energy is involving in this situation, right? So the energy related to this situation is called spring energy. We call it ES. And that is given to you as half K x squared. Proof is not needed. You need calculus to prove that. So unfortunately, we don't have that in our syllabus. So then we avoid looking at the proof, but we remember. Spring energy. So we call this spring energy. Right? So that means half K x squared amount of energy, of spring energy, or you can say of energy, is stored inside the spring due to x amount of extension. Okay, now you understand that. We will try to go deep. Think about this situation, which is the rest length. The spring is at rest, nothing is attached to it. So then you will understand x is going to be 0 in this case, because x is measured from this onwards. X is 0. X is 0 means Fr is going to be 0 automatically. Why? Because Fr is equal to minus Kx. Then spring energy is going to be 0, because half into Kx squared. So for a rest spring, you don't see anything. It just rests. Now you try to give a small extension to this. You try to give a small extension to this. Suppose this is going to be x0. Now, on this spring, x is going to be x0 now. On that spring, you will have a restoring force, which is minus k x0. K should be given to us. K is a constant. It's a material dependent constant. In the exam, it should be given to us. So restoring force is minus k x0. Then what about the spring energy? That's going to be half k x0 squared. because x0 is the extension from the rest position. Now, for this situation, we understood the force involvement and energy involvement. So if you have a physical situation, system, if you want to think about that system, you can think about the forces, you can think about the energy, right? So I'll give you a small note here. The connection between force and energy, I taught you before, which I'm going to remind you. Relationship between forces and energy. So you have to understand these two are two different things. So force, energy. So these are two different things, right? So the connection is through work done. Connection is through work done. And then work done, we can write W is equal to force times displacement, right? That is one way of finding work done. The other one is work done is equal to W. Kinetic energy difference, delta EK. Kinetic energy difference. So that is nothing but half into mv squared minus half into mu squared. That's the second one. Kinetic energy difference. So now we define this work done in terms of force and in terms of energy as well, right? So the connection is the work done, you can relate these two. So work done is F times displacement, and this one is going to be kinetic energy difference. We call it kinetic energy difference. So that's the connection. Okay. Now, what we understood, if you have a system, you can talk about forces, you can talk about energy. Two things we have. What is the connection? This is the connection. Very important fact. Now let's go to our system. When we go to our system, you can see restoring force is available to you, and the spring energy is available to you. But these two are there when the object is at equilibrium. Object is not moving at this situation. Can you understand? Object is at stationary. At equilibrium situation, object is at stationary, right? So object is not moving here. So in other words, object is not moving, that means at equilibrium. Okay. Right. Now let's think about mechanical energy. Right? So I'm going to revise mechanical energy. I would say revision here. because I need to use that concept here. Mechanical energy. What is mechanical energy? Mechanical energy is kinetic energy plus gravitational potential energy, right? Gravitational potential energy. So, if you think about a system, like this, right? So, let me duplicate this one. Right. So, think about the object is at this position. U is the U1, for example. U1 is the speed. Think about the speed at this point is U2. Think about the speed at this point is U3. Right? So, same thing here. U1, U2, and U3. Now, height is involving here. What is involving? Height is involving here. Right? So, that means gravitational potential energy is involving here. If the height is involving, the gravitational potential energy is involving. Now, we understand this as a fact. When you are dealing with gravitational potential energy, you have to define your gravitational potential energy zero line, right? So, in the first picture, I'm going to consider this line to be gravitational potential energy zero line. For the second picture, I'm going to take this to be gravitational potential energy zero line. So, I would say here, EGP is equal to 0. I'm going to consider EGP is equal to 0. So, this is your decision. You can take this decision the way you want. Now, think about the height from here to here is going to be h1. The height from here to here is going to be h2. So, if you think in that way, you will understand the height from here to here is going to be h1 minus h2, right? And the height from here to here, h2, right? So, height is h2. Now, let's try to find out, or let's try to write the mechanical energy here. So, what would be the mechanical energy here? Half into mu1 square, that's kinetic. What would be the potential? Potential, you are calculating h1 in the vertical up direction, which is going to be positive. So, it's going to be mg h1. Agree? For the other situation, it would be half into mu2 squared, but potential is 0. Why? Because you are sitting on the gravitational potential energy 0 line. At this situation, half into mu3 squared plus mgh2. Agree with me? Now, what you know here, this energy should be equal to this energy, should be is equal to this energy. What is that concept? That concept is called energy conservation. Energy conservation means if you pick one point, the total energy at that point should be equal to the total energy of another point. All good? Now, let's think about the second situation. Second situation here, it's going to be half mu1 squared. Kinetic is fine. But your potential is now mg h1 minus h2, isn't it? Right? So this one, half into mu2 squared. Now, what is the potential? So you're measuring it vertically down. So it's going to be minus mg h2. Agree? Right. So what about this one? This one is going to be half mu3 squared plus 0. So similarly, these three equations or expressions should be equal to each other. Energy conservation. So we understood how this energy conservation works, and then I revised it already. Yeah. Now we are going to understand. So I'm going to give you the introductory part only today, right? Because I'm not in a hurry to finish this in one shot. You have to understand, when it comes to this linear spring, this situation is all right. It's not a big deal. This situation also fine. Why? Because once you attach this object, it comes to an equilibrium situation. Equilibrium situation means this is steady. This is not moving. That is steady. Right? So for this situation, we discussed about forces and energies. What is that energy? This energy is called spring energy. That energy is stored inside the spring. Force is the restoring force because of the attached mg. Yeah. So we understood this. Now, next part is we are going to perturb the system. Perturb. Good. It's a good word. Perturb. In chemistry also we have this word, perturb. We call it perturbation. Perturbation means disturb. Perturbation means disturb. So now we are going to perturb the system. Means we are going to disturb the system. Now, what do you mean by disturb? You always disturb a person who is at equilibrium. You are going to perturb a person like a person who is at equilibrium. Right? You are going to perturb a calm and quiet guy. Right? So, how to perturb the system? Obviously, to perturb the system, you need to somehow drag it. You are going to drag it and then release it. In perturbation, what you do is you give a small kick, like there is a football, soccer ball, stationary. You want to perturb the system. How do you perturb the system? You give a small touch. You are playing carom, carom, the carom disc is there. Disc is at equilibrium. I mean, not moving, nothing. So you give a small kick, you perturb the system. So likewise, you perturb this system. How to perturb this system? You try to pull this a little bit, a little bit. So when you pull this one a little bit, what will happen? Your perturbing the system means you are disturbing the equilibrium. What will happen if this is a linear spring, ideal spring? This object is going up, down, up, down, up, down, up, down, up, down, up, down. You can experiment this. Take a rubber band, attach something. You can observe the equilibrium. Okay, it's at equilibrium. Stretch it a little bit, release it. You can see that object is going up, down, up, down, up, down, up, down, up, down. Right? So this motion is called simple harmonic oscillation. You understand oscillation, the term oscillation, you understand. We call it simple harmonic oscillation. So this oscillation is the most fundamental oscillation. So we have a lot of assumptions. No air resistance, spring is linear, ideal, right? So this is called simple harmonic oscillation. Another example for simple harmonic oscillation is, you might have seen father's clock. We call it daddy's clock, or what do you call that? Father's clock, grandfather's clock. Yeah. So there you can see that pendulum, right? Goes this way, that way, this way, that way, this way, that way. That motion is a simple harmonic oscillation. So that is oscillating through what? That is oscillating from the vertical, going this way, that way, this way, this way. So that's a simple harmonic oscillation. Now you understand this simple harmonic oscillation is like a sine curve, math people. Sine curve. Sine curve, half of it is up, other half is down. So simple harmonic oscillation, up, down, again up, again down, again up, again down. So it's a sinusoidal type of a oscillation. So when you go to university, not in VCE, when you go to university, simple harmonics oscillation you are going to model in engineering. When you are modeling that, you will see they are going to construct that simple harmonic oscillation through sine curve or cos curve. And you have to understand why, because it's a repeated period. Right, okay. So now we'll try to disturb the system now, okay? So topic, simple harmonic oscillation. Right. So in this part, I will show you the picture only. Okay. Now look at this. This is my rest length, L0. This object is attached. This extension is x0. So this is my equilibrium. This is my equilibrium situation. Now I'm going to pull this. How much? X amount. So this is x0. I'm going to pull this a little bit. Why I'm pulling it? To perturb the system. Because of that pulling, this object is doing a motion, this type of a motion. It's a simple harmonic oscillation, right? After perturbation, the system shows a simple harmonic oscillation. Simple harmonic oscillation. So at that situation, x0 should be greater than x. So how much you are going to perturb? A little bit. So x0 is greater than x, right? Compared to x0, the amount you stretch is very little. Then only you will see a simple harmonic oscillation. Right?